Good evening, everyone. Thank you for sharing. A pleasure to speak today at the Neighbor Nights organized by the Angregs. And I'm Esther. I'll cover the first half of the talk today, and then Layla will gently take over and present the second half. And we hope you get to know better about CINet Junior Scientist Council after this talk. So we are a group of graduate students and early career scientists associated with the Critical Interface Network project. It provides opportunity to develop network within CINet field and also with the scientists in other institutions. And in the next slide, we'll cover the concept of CINet in more detail. So if you can go, yeah, thank you. CINet Junior Scientist is a council, is a part of CINet Project, which is funded by National Science Foundation, known as NSF. And the whole CINet projects include university partners, such as University of Illinois, University of Tennessee, Northwestern University, and more, as shown in the slide. Also, we work together with Prairie Research Institutes and, of course, the National Great River Research and Education Center. And although there were annual in-person CINet meetings in the past, the CINet Junior Scientist Council started last year during the pandemic period. So the only group picture that we have is a screenshot of us on Zoom as shown on the top. And although all of our meetings were held virtually, we were able to successfully hold three monthly pop-up webinars and participate in weekly writing groups and share the resources related to professional development. Also, as part of the group, we help the field work to promote safety and gain the field experience. And let's dive into what is CINet. CINet is short for Critical Interface Network, where the critical zone is the living, breathing, evolving interface between rock, soil, water, air, and organisms. And it spans treetops to the aquifers far below our feet. And the complex interaction over time govern the critical zone architecture and the availability of the life-sustaining resources. So in other words, we can think of the critical zone as the living skin of the earth, and we want to understand how it is structured. So for example, we look at vegetation above the surface and the root environment below that, and the soil environment, and then the water percolating through the soil and the rocks at the bottom. And we get loss of the soil from erosion at the top, but we also get the soil formulation from the rocks through the weathering processes. So over the long terms, the erosion is balanced with the weathering and there is tectonic uplift. So we don't see much change on the surface, but we see loss of active soil and the generation of the soil. And the rocks, when they weather, they create the minerals, and when they dissolve in water, they are taken up by the plant's roots, and that supports the productivity of the plants and the vegetation. And also the growth of the plant roots and the vegetation determines the soil structure. So when we think about critical zone, it is the whole feedback process. It includes the whole feedback process between above ground and the below ground. And the time scales associated with those above and below ground processes are quite different. So for example, the conversion from the rocks to soil takes a long time, but the vegetation grows and dies in much shorter time scale. So there is a slow interaction in these complex processes in the critical zone. And this critical zone study started with the idea that if we could make measurements of all those connected processes simultaneously, then we will be able to better understand how those linkages and the landscape function as a whole. And the study of critical interface started in 2007 when NSF, the National Science Foundation, started funding those observatories as shown in the map at the top of the slide. And currently there are 9 observatories in the US in many different environments to study Earth's outer skin. And especially in the central US, there are 3 observatories that are labeled as IML, which is the intensively managed landscapes. When we say intensively managed landscapes, we essentially mean that the human activity dominates those landscapes to a very large extent. So the functioning of that landscape is pretty much determined by the human influence as compared to the other sites, which are more natural. So the other sites also have human influences in terms of climate change and so on, but in IML sites, there is an interaction between the climate change and the human influence that affects the whole ecosystem. So as a group, we are working to understand how the agricultural activities influence the critical zone processes and the soil functions and its health. So as I mentioned before, the critical zone in intensely managed landscape is a highly dynamic system responding to the confluence of the stressors arising from human action and climate change. So we focus our research activities on 3 critical interfaces that are exceptionally important to the critical zone that are strongly affected by human action. So the first one would be the near land surface, and the second is the active root zone, and the third one would be the river corridor. So in the following slides, we will cover those 3 topics in more detail. So we investigate the dynamics of the near surface critical interface to determine how human activity and the weather and climate events control agricultural activity and how it also affects the soil functions and its health. So if you look at the pictures at the top in the middle, this is after we harvest the corn. So the field looks like, shows the soil. And farmers would go in with the equipment and tilt the field. And it will take the straws and mixes with the soil. And if you let this process occur naturally without any human intervention, then it would take much longer time to decompose and mix with the soil. However, as a result of this mixing from the humans, this field become more prone to erosion since the soil structure is now in a state where the structure is easily broken. So as a result of human activity, there could be destruction of near surface macro pore structure, and it also could impact the soil carbon storage. And also in the intensely managed landscapes, there are large agricultural lands covered with soybean and corn. And there is a flux tower measuring atmospheric and ecohydrologic variabilities around the tower, which would provide data to study the interplay between the agricultural crops and the climate variability. And those CO2 fluxes are measured from the tower, as you can see in the picture at the bottom. And the measurements, CO2 measurements that are measured from the tower are affected by the footprint of the flux tower. And the flux tower varies depending on the wind speed and the wind direction, and also by the composition of the soybean and the corn mosaic around the tower. So as part of the project, we study the variation in vertical and horizontal micro topography and the soil micro and macro structures and surface roughness and the depression and the mosaic of vegetation patches associated with agricultural fields. And if we are better informed and we can manage these landscapes at much finer granularity with improved methods to interpret the field measurements, then we can get a better estimates of the productivity of those crops in those landscapes. And the active root zone critical interface includes the study of the soil root microbe system that mediates mediates the subsurface hydrobiogeochemical environment in conjunction with the surface dynamics that are primarily controlled by tile drains and the artificial ditches. So in the IML sites, we have created the tile drains. These are the perforated pipes installed every 30 to 40 meters across the whole Midwest, including Minnesota, Indiana, Wisconsin, Ohio, and Illinois. And these tile drains exist all over the place to drain out the water from the land and sometimes they also flow with the sediments. And in the picture at the top, which is taken after the storm, you can see that a lot of water are flowing out from the tile drains into the river. So if you think about the natural movement of water versus those tremendously modified flow through the tile drains, there are high impact from the human activity, not only in the water flow, but the residence time of the water, but also on the water chemistry. However, we use this tile drainage to manage the hydrology of the landscape, which helps reducing the flood damage and which helps the crops to survive. And also as part of the critical zone study, we examined the river corridor critical interface. The river corridors, which include the channels and floodplains, those are distinctive critical interfaces that represent important transport and transformation processes linking uplands to depot centers. And the river corridor critical interface behaves as a biogeochemical reactor and critical zone filter that affects the trading of fluxes of water, nutrients, sediments among uplands and floodplains, channels, and downstream depot centers as far as the ocean. And as part of the project, we installed the corings from the stream edge to the hill slope to study the micro-topographic characteristics and the root zone structures and the river valleys, which are the major factors influencing the transport and the transformation of sediments, carbon, and nutrients within river corridors in IML sites. And as part of the CINet project, we have been developing these models where the vegetation processes are coupled to the full 3D structure of the subsurface transport, which is coupled to 2D surface water transport. And this model is different from other traditional hydrology since this model allows the water to get into the topographic depression and stay there, which impact the whole biogeochemical processes. And these subsurface modeling with embedded tile drainage allow us to characterize the process in more detail. And in the bottom left figure, it is a results from our model, and it shows that every variation that you see in this figure is driven by the topographic variation associated with LiDAR-derived DEM. It is the result of uniform rainfall simulation. And in there, you'll also see the effects of tile drainage and the drainage systems. So using this model, you can also study biogeochemistry by looking at spatial distribution of nitrogen age and nitrogen concentration in order to examine the effects of the tile drains on nitrate fertilizer. This study could guide the precise application of fertilizers that would reduce the amount of fertilizers that are applied in the farmland. And also it could help maintain the productivity and reduce the efflux of nitrates going into the stream system and affecting our environment. So the reason we study this, we work on this project is that our project aim to expand the scientific understanding of critical zone interfaces that are responsible for the sustainability of our agricultural environment for the betterment of society and national and global economies. In particular, the project aims to help create precision agriculture and guide the future agricultural practices. And the findings will also help inform restoration ecologists of the long-term responses in soil function in agro ecosystems to guide their future works.
Good evening, everyone. My name is Leila Hernandez, and I'm going to continue with the presentation. So, CINet Project consists of a network of core, satellite, and supported sites in the glaciated parts of the Midwest and outer reaches of the upper Mississippi River Basin. These regions contain some of the most productive but intensively managed landscapes in the world. The two core sites are two watersheds. The first one is the Upper Sangamon River in Illinois, and the second one is Clear Creek in Iowa. At these sites, we integrate research efforts across all three interfaces, as Esther showed. These core sites have well-established observational infrastructure, accessible field sites, and a wealth of knowledge collected through the IML-CCO and prior effort. In the next slides, I will show you some of the specific sites where the project is going on. So the first site is the Sangamon River Forest Preserve, which is located in Fisher, Illinois, which is about 30 minutes drive north from Urbana-Champaign. The goal of the natural preserve is to restore the landscape as closely possible at its original pre-settlement conditions. The observation site is located on the eastern edge of an upland and extends onto the floodplain of the Sangamon River, as is shown in the figure up to the right, which also shows the lidar elevation on the Sangamon River Forest Preserve and the location of the 2015 baseline soil sampling sites. This site has been in cultivation for more than 70 years until 2007, when the land was received back into prayer. In this site, our group installed a weather station which operates since 2014 and groundwater monitoring wells. The deepest wells monitor groundwater levels in regional aquifers at various depths down to 100 meters. The shallow wells measure seasonal changes in the near surface water table. And the weather station has been used in research to better understand how individual ecosystem processes respond to large-scale behaviors, such as responses to droughts, weather events, or human impacts, also using an information theory approach. This site is also one of the three weathering profile observatories installed in the IML project. The other two are located in Iowa. The second site is the Flax Tower site at Cuzz Creek, which is in Illinois. The site lies on a low relief upland and has been ditched to drain fields during the wet season. To measure land-atmosphere interactions of ecohydrological fluxes in this intensively managed region, the IML-CCO project installed this tall flux tower, which is 25 meters tall, and that is about 82 feet. The Flux Tower started collecting data in 2016 and is specifically located at the edge of an agricultural field that rotates between corn and soybean. At the very top of the tower, there are instruments that measure hydroclimatological variables at high frequency, such as wind speed and air temperature, which are used to estimate the vertical flux of water, energy, and carbon dioxide from the surrounded area. The location of the area that the tower can see depends on weather conditions, and it can be as far as 10 kilometers away from the tower. In the same flux tower at 10 meters high, the project also measured other ecohydrological variables such as solar radiation, air temperature, NDVI, relative humidity, and wind speed. Also, there are sensors to measure soil moisture, electrical conductivity, and soil temperature at depths of 5, 15, 30, 50, 100, and 180 centimeters depth and in a location adjacent to the tower. And also the project has ground heat flux plates to measure ground heat flux. In addition, the project also installed a tipping bucket to measure rainfall. And together, all these data provide a detailed picture of ecosystem fluxes and the energy balance over a relatively large footprint. The next site is the Gans Farm Field, which is a 25-acre triangular plot under corn and soybean rotation. The plot has a subtle topography with a low gradient from north to south. The site lies in an area of geographically isolated uplands and depressions that have been hydrologically connected through surface ditching and a system of buried field tiles. This low relief interconnected landscape provides an ideal setting for a comparative study of soil organic carbon variability, as well as hydropedagogical processes. In one of the studies, for instance, that use data from this site, the researchers found that the concentration of soil organic carbon inside the isolated depressions were generally higher than surrounding areas outside of the depressions. The fourth site is the Cuzz Creek Isco site, which is a gauging station on Goose Creek near Dillon, Illinois, which is required to acquire flow data to develop a rating curve for this tributary and is used to measure the impacts of channel maintenance on sediment fluxes within the headwater channels. The field instrumentation is an Isco automatic water sampler, which was installed at the bridge over the Sangamon River to collect river water samples at predetermined frequencies. The drainage ditches in the headwaters are managed by drainage districts, which are local governmental units. In 2015, the district commissioners decided that the ditch and in the headwaters needed maintenance and excavated the channel to remove vegetation and accumulated sediments from the bottom of the ditch. And that is what is shown one of the pictures in the slide. The last site that I'm gonna present today is the field site that was established just outside Montecito, Illinois, to measure water and sediment fluxes from the tile drains into the stream. The site lies along a low gradient tributary of the Sangamon River and is characterized by its poorly drained low soil. The Allentown Transform is owned and managed by the Board of Trustees of the University of Illinois and has been the site of natural resources research activities for many, many years. It uses a Isco sampling device and tile drained waters and sediment samples, which are collected through rainfall events. The water samples are collected and processed by the Illinois West State Water Survey and then sent to Purdue University for isotopic and nutrient analysis. The resulting data has been used also by several researchers to better understand the carbon cycle as well as nutrient loss through tile drain flow. So the CINet project is happening now. The research will take place from 2020 to 2025, and it's part of a large critical zone collaborative network. This program is the successor of the Critical Zone Observatories program. And as part of the activities of the project, CINet is developing a comprehensive educational and outreach network focused on infusing emerging research into the development of K-12 curricula. So also is investing in higher education programs through university partners, also stakeholder outreach activities, such as extension services, and also a transdisciplinary based external program evaluation. And as Esther mentioned previously, the Junior Scientist Council is an initiative created by the grad students in the group to promote networking and mentoring among junior and more experienced scientists. So the Junior Scientist Council of the CINet currently have two main activities to the public, open to the public. So the first one, as Esther mentioned, is a monthly pop-up webinar series, which is a space where we invite one or two speakers to share their research progress. The format of the pop-up webinar is very concise. The idea is that each presenter has only one or two slides where they convey the majority of the information and they explain the topic in 15 minutes, which allow us to have more time for Q&A discussion and during the session. This space is open to all levels of expertise, so we try to pair one student and one more experienced researcher in each session. And the idea is to practice our abilities to communicate our research to the community, which is one of the ultimate goals of the scientific project. The second activity is the coffee chat, which we inaugurated last October with the presentation of Professor Jen Henstra, where the idea was to discuss topics that impact the well-being of grad students, as well as to provide resources to explore career paths and prepare us as early scientists. So we also have active social media accounts on Twitter and YouTube, where we share the results of our activities. So if you are interested in knowing how we as grad students are contributing to the efforts of the CINet project, we welcome you to follow us in social media. So finally, Esther and I greatly appreciate your invitation to this monthly neighbor night. And we hope that you have enjoyed knowing a little bit more about our project, about the CINet project. And if you have any comments or questions, we are very happy to take them. Thank you.
Thank you for such a great presentation. It looks like there's a couple questions in the chat, so I will read those out. One, can you tell me the reason why we're comparing restored landscapes such as Site 1 to agriculture sites? So what do we hope to gain when we compare a more natural landscape to an agriculture site?
I'm gonna go ahead and answer that question, even if it's not my research focus. It's not my research topic, unfortunately. But I think restoration is one of the biggest scientific inquiries of this kind of research. So having the opportunity to compare a restored place with other places that are under intensively managed intervention gave us the opportunity just to explore if those solutions or those activities are actually impacting, and to what extent are impacting, how quickly we can see a transition from how it was to how it is now. But I wish I have a better answer to that. So if any in the group is here and want to go ahead and answer that, I'll be very happy.
Is it okay if I jump in?
Yeah, you're more than welcome to, Praveen.
Yeah, hi, I'm Praveen Kumar. I'm the lead PI on the project. That's a really good question. I think a lot of us are, one of the key goals of the project is to make sure that the landscape, which supports so much of economic activity and agriculture, remains sustainable over the long term. And so we have converted this landscape, which was basically prairies, to agriculture over the last 200 years. And we don't have a very clear understanding as to what the trajectory is. Is it sustainable? Is it unsustainable? What will it take for this sustainable? And how can we guide the agricultural practices in various ways to ensure that it is both economically profitable for the farmers as well as sustainable over the long run. And so to get to that, we need to basically look at different states of these landscapes. So one is where we are farming now, and then by comparing it with areas that are not farmed or restored or forest systems, we get sampling of what's going on in these different landscapes. And one of the things which we will also do is not just study things that are in Illinois, but as it was said earlier, various other areas like Iowa and Tennessee and Minnesota and Nebraska, to see how these differences manifest over climates or different types of landscapes. So Iowa, the landscape is more rolling as compared to Illinois. Nebraska is much drier than what is here. So our goal is essentially to get a much more comprehensive understanding of what is going on and how different component landscapes are connected, how they serve as sources of material that is transported, and where are they deposited, and for how long are they deposited, and so forth. So the goal is to basically get a pretty comprehensive understanding. So we can use the science to inform potentially sustainable practices. So I see those questions. Our goal is not to place blames on any particular community like agriculture or industry or so forth. I think that's not the purpose. The purpose is to really scientific point of things. We want to figure out what is going on and if there are ways for us to optimize. If there is a way for more precise application of fertilizers, as an example, could we inform that so that technologies could be developed which are economical as well as sustain productivity? So I think it's a very scientific investigation rather than any particular uh, approach to finding who is responsible for anything. That's not the goal. So thinking down the road, what kind of benefits and applications do you see coming? Yeah, basically, we see that potentially we can inform the agricultural community for better practices in the scientific community in more nuanced things that may be going on in the landscape. So for example, if you look at trends of change, the climate change or rainfall pattern change or more warming, will it keep the carbon in the soil or the nutrients in the soil, and will the plants grow just as healthy? So those are the kind of questions in there. Is it okay if I just quickly run through all the questions here? In terms of sampling, are there any comparisons between restored sites and remnant sites? The answer is yeah, we're trying to find remnant sites. I mean, we're having difficulty finding sites that are historically natural. So we have to some extent, rely on restored sites. The remnant, so it's not just the comparison of remnant sites versus what's going on. A lot of things there, right? You have to have the similar soil type and so forth. So that makes site selection challenging, but we are exploring all those options. Is you have to make predictions about potential benefits of improving soil health on hydrology? Yes, one of the things which we want to do is look at soil health and the interaction between soil health and water transport and nutrient transport, and see how we may improve the dependency in there and enhance productivity at the same time.
Awesome. Thank you for helping out with the questions, Praveen. Are there any other questions anybody has? You can feel free to type them out. You can unmute yourself and say them out loud if you'd rather do that. And since this is actually part of our CINet grant, I'm going to post a survey in the chat. Please take the few minutes it takes to complete the survey. This is going to help us with the grant moving forward and create better learning opportunities for the community. So I will add that to the chat. It will also go out in an email that will either go out this evening or tomorrow morning. So just feel free to do that whenever it's convenient for you.
There was one more very important question in there, which is basically how are you communicating your work with the farmers? One of the goals we have is to basically engage with different stakeholder groups in there. And we are also basically working with our extension program here. And the idea is that we provide the findings through short courses that the professionals through the extension program can and digest and communicate that in an effective manner. So that way, I think there is definitely a vetting process that will happen as to what some of the findings mean and how they can inform agricultural practices and how they can be adopted. So we are going to be pretty active in making sure that this continues through the duration of the project. And it's not just a one-way street. I mean, one of the goals is to get feedback on the kind of findings that we are making, or whether they make sense. Are they adoptable in there? Are there challenges associated with this? Will they affect anything in an adverse manner? So that we can look deeper into that. So we need to have a two-way communication with the community and the stakeholders.
Thank you. All right, any last questions anybody may have? All right, if you have no other questions, thank you again for joining, and look for some more information about our February neighbor nights. We're going to be talking to our Habitat Strike team and learning about prescribed burns and all the work that they do in the region.
Thank you so much, Jen, for putting this together. And thank you, Layla and Esther, for participating, and Praveen for fielding those questions for us. I'm really glad we were all able to come together tonight, and I really look forward to seeing you all at the third week in February event. Thank you.
All right, have a wonderful night, everybody.